Hello, folks. Professor Fiore here. Guess what we're going to talk about today? I think it's an audio compressor. What are we talking about? What's an audio compressor? Well, essentially, an audio compressor smooths out the volume levels, the variations in its output signal, in spite of changes to the input level, right? So as the musician plays, let's say, or maybe a person is speaking or singing, maybe there's a little bit too much in the way of dynamics there, and we want to make this a little bit more consistent. Sometimes we do this on some instruments like bass or guitar as an effect, maybe to increase sustain, for example. All right, now typically this would be measured in terms of a compression ratio, and you can think of this in terms of squashing down the input dynamic range. In other words, normally with an amplifier, if you had, let's say, a 6 decibel increase in the input signal, the output will increase by 6 decibels. In other words, you double the input, you double the output. Whatever that ratio happens to be. 3 times input, 3 times output. With compression, if you had, let's say, a 6 dB input change, maybe that only turns into a 3 decibel output change. We would call that 2-to-1 compression, right? Maybe a 10 dB input only turns into a 2 dB output change. So that would be a compression ratio of 5-to-1, all right? Now, one of the important characteristics is how the compressor responds, how quickly it responds to changes in the input. And this is typically measured in terms of an attack time and a release time. How many milliseconds for the compressor to actually stomp on the input signal, so to speak. And if it's kind of slow, you might wind up with sort of excessive attack, which, if you're a bass player and you want a really, snappy kind of sound, you might like that. And then on the release time, how long does it take for the gain to sort of go back to its nominal level? If you're not careful with this, right, if you do too much compression, you can wind up sort of squishing the life out of the sound, right? It'll become dull. The sound won't be very expressive dynamically. So you have to be careful about that. And as the gain changes, sometimes the background noise, hiss for example, will be going up and down along with your signal. And you can get effects called pumping or breathing. So if you just listen to this, it sounds like, the sound itself is sort of breathing. It's breathing in and breathing out and breathing in and breathing out. So we have to be a little careful about those kinds of things. Now, what we're going to look at is maybe something a little bit different than what you typically see. If you search around on the internet, it's very common to see compressors made one of two ways. Sort of the biggie is we use a light-dependent resistor, basically a resistor like cadmium sulfide cell, that the resistance is inversely proportional to the light level. So you get a lot of light, the resistance goes down. You get very little light, resistance goes up. So what we'll do is we'll take the input signal, run it into a little amplifier or something like that to crank the signal up. We'll drive a little lamp or an LED, something like that, so that as the signal goes up, the light source gets brighter. We encapsulate that with the LDR, right? So no outside light gets in. So as it gets brighter, that resistance goes down. We use the LDR as part of a feedback loop in an amplifier. So as the signal gets larger, the light gets brighter, the resistance goes down, and the gain goes down, right? That's a very basic idea of doing that. You can make very simple compressors using that idea. Instead of the LDR, another way to approach this is through a JFET. You can use a JFET in the ohmic region, right? So it acts like a voltage-controlled resistor. And I have some videos on of using FETs in the ohmic region, so you might want to take a look at those. It's basically the same idea as the LDR version. But I want to look at something different. We're going to use an OTA, an operational transconductance amplifier. And I do have a video earlier in the op-amp playlist that specifically talks about the OTA, and you really should take a look at that. Read the section on the OTA in the free textbook, right? My free op-amps textbook that you can download. I am not going to go into the details of how the OTA works. As a matter of fact, I'm going to use a circuit that's The OTA part of it is only very slightly modified from the version that I have in the OTA video. So I'm just going to kind of, look at what comes next, so to speak. And the key thing I'm going to say right up front is we need some way of taking the input signal and turning it into a DC level, a slowly changing DC level that corresponds to the volume. Now, you can get fancy with this, or you can be fairly simple, Sometimes the fanciest way is not necessarily the best way. Let's take a look. All right, up here is the OTA. I'm using a 13700 OTA. Like I said, this is very similar. If you look at the video on the OTA, it's almost the same. I am not showing an input buffer. If you're going to use this with a guitar or a bass, a passive anyway, you're probably going to want to have an input buffer back here because this thing only has a 30K ohm, roughly 30K ohm input impedance, which isn't really high enough for a passive guitar or bass pickup. So you'd want that out here, right? Right there, as a matter of fact. But I want to keep this a little on the simpler side. Now, what you might recall about the OTA, at least in this configuration, is over here, our ABC in conjunction with VC, which is a control voltage, sets the gain of the amplifier. The higher the control voltage is, then the IABC, the programming current, increases and we get more gain. So the bigger this voltage is, the more gain this amplifier produces. Okay? Now, I've set this up for a signal that's maybe no more than about a volt, which is what you would expect on like a guitar or a bass typically. Depending on what you're using, you might want to do some mods over here on the front end. But in any case, what we want to do right now is really look at the control voltage, because what I'm saying is if I want to compress the signal, then the bigger this input signal is, the smaller, or the more negative, however you want to look at that, VC should be, because that will give me less gain, right? If VC is 10 volts, I'm going to get a certain gain. If it's plus 5 volts, I'm going to get less gain. If it's 0, I'm going to get less gain than that. And if it's minus 5, I'm going to have very little gain, right? So I want to take this signal and somehow determine what its volume level is. Now, we're not going to do this perfectly. What we're going to do is essentially use the voltage peak level as a proxy for its loudness, right? That's not perfect, but it'll work for our purposes. So what we're going to do, first of all, this might look familiar. This is a precision rectifier. It's actually a precision rectifier with gain. Okay, if you look at the precision rectifier video, you'll see that I start this off with just a simple unity gain buffer here. Essentially, the feedback compensates for the forward drop on the signal diode, so we don't have to worry about the 0.7 volts. Without these resistors, if you just had this straight wired back, the output right here, okay, would essentially be the positive half waves of the input. That's it. Now, I've added the gain here so that we have some control over the compression level. Typically, you would make RF a potentiometer. All right, so you might just make this a 100K pot, wired up as a rheostat. All right. So what we would get essentially is a half-wave rectified signal. Now, the capacitor, C2 over here, is essentially used to filter this out. This is sort of a peak hold capacitor. And what will end up happening is, as the input signal comes in, right, you're going to get this really rapid kind of thing, and like you pluck a string, and then it's going to die out. So this cap will charge up very quickly because the op amp is going to be treated as a current source. So it's going to rise up to that peak level and then slowly drop off. And the speed of that, which essentially is the release time for this compressor, is controlled by C2 and R1. That time constant will set that up. So you could, for example, switch in different values of C2 to get slow and fast release times. All right. You could also alter R1, the input resistor here, but if you do that, then you're also going to have to adjust R3 because this is going to set up a gain for this second op amp, which I'll get to in a sec. So you might just want to have some caps there, on a switch, so you can have 2 or 3 settings. You might, if you're using this for like a guitar and it's a, a purpose kind of built circuit, and my suggestion right up front is breadboard the thing, try it, get the values that work best for you, and run with it. It doesn't really matter how well this thing works out on paper, how well it simulates. Ultimately what matters with these audio circuits, especially things like this or fuzz boxes and EQs, what matters is how does it sound, right? What are your ears telling you? If it measures, quote unquote, great, but it sounds like crap, it's a useless circuit. What matters is how does it sound, right? I'm not even like hyper concerned about the distortion on this because, again, if you're going to use it for a guitar, you might actually like the little bit of distortion that this thing puts in. All right? Okay. In any case, so that sets that up. So what we're going to get now, instead of just half waves, we're going to get this sort of peak, and then it's going to kind of slowly drop off. All right? And that voltage then goes into this inverting summing amplifier. So that turns into a negative, right? So if here's your 0 level, that's going to come down, it's going to go negative, and then work its way back towards 0. And that voltage is, the output, is the control voltage. So if I have a large input signal, right, I'm going to get a large peak value out here, which is inverted. So that's going to give me a more negative value out here. And as I said, the more positive the control voltage is, the bigger the gain is. So in this case, big input, we get a more negative output because of the inversion, and the gain goes down, which is exactly what we want. Big signal, small gain, small signal, big gain. All right, so the pot down here basically creates a bias. It creates a DC offset. So you can kind of fiddle with this, and this will adjust the entire range of this. Now, if you don't have this at all, like if you just got rid of this, like you got rid of R2 and P2, the minimal value out of here, actually the let's call it the 0 signal level, would be halfway for VC. VC can essentially vary between the power supply rails. Not quite, but pretty close too. So you'd only be using half the range, all right? This creates a little DC bias, so you would have this biased slightly positive. In other words, so that when there's no input, VC would be, some modest positive DC value, maybe 5 volts or 8 volts or something like that, depending. The more you bring that down, then the larger the range of input where you don't really get any appreciable compression. Now, this circuit is actually set up as kind of it's kind of along the lines of what's called a soft knee compressor. A hard knee compressor is basically if you plot the input and the output signal, right? It kind of goes up, it's all nice and linear, and then suddenly you hit the threshold level and boom, it kind of flattens out. You get that compression ratio I was talking about, right? It's 1-to-1, and then boom, you hit compression. Soft knee kind of goes like this, right? It's a smooth curve where there isn't an obvious point of inflection. That's more like what this circuit does. But you do have some control over, exactly what the range is, how much compression you're going to get and where it starts with P2, but primarily with this RF value. The more gain you give this, the greater the effect is going to be, right? This is not what I would call an extreme compressor. If you really want to stomp on something, this is maybe not the design you want. This is, more of a basic kind of leveler, not so much an audio limiter, all right? But anyway, let's take a look at what's going on here, okay? So my signal source is a 250 millivolt peak signal at 1 kilohertz. And we just want to see what the gains are going to be as I change this input. Right? What do we see at the output? Oh, by the way, if you're wondering about P1, I'll just remind you, P1 there is there. You can tweak that to adjust a little DC offset that you might get at the output. And in our output, since I've just set this up for 50%, I left it in there just as a reminder, right? For those of you that might be breadboarding this, we are going to see a small DC offset at the output. Don't worry about it, okay? Anyway, let's see what we get. I'm just going to do a simple transient analysis over here. So I'm going to run this from 0 up to 20 milliseconds. So given this time frame, right, 10 micro and 22K, that works out to 220 milliseconds for a time constant, right? So, we're talking about half a second for this thing to really fall the majority, from its peak value, all right, for decent sort of release time. Let's see what we get. All right, I'm going to bring this down here, open it up a little bit more. And I am going to separate out, well, let me get the legend down here first. So we can see VC is the control voltage, this maroon thing. Looks kind of funky. And then the darker green is V load, okay, the output. And then the sort of olive color is the input voltage, right? So this one right here that I got the crosshair around, that's the 250 millivolt peak signal. And we can see that the output signal, the darker green, is a little bit smaller than that. So I'm going to separate these curves so we can see them a little better. All right. All right. So what's happening here? Well, this bias is set up. I think I have this at like 40% or something. Yeah, 40%. So, the total range, this pot is going from plus to minus 15 volts. That's a 30 volt range. So there's like a 10% of that, or about a 3 volt bias. Okay. So this is set up for a gain of 1, 22K, 22K. So there's the 3 volt bias that we have, the plus 3 volt bias, because that's negative and it's inverting. So I get plus 3. Now, as the input signal comes in, this, like I said, rectifies it. And what we're seeing here is this capacitor, okay, jumping to that value. And then over time, like I said, it kind of levels out. All right. So this is not much. This is pretty close to 0 volts. We're kind of like at this essentially halfway value on the gain, right? Because we could crank VC all the way up to nearly 15 volts, my power supply rail. Not quite, but close to. So we're kind of like right in the middle. But in any case, let's check out what our gain is, right? What is the output signal? All right, so the peak value on here is like 166, 167 millivolts. All right, and if you look closely, you can see that there is a little bit of a DC offset here. All right, you can see just on that distance. Like I said, don't worry about the DC offset. It's sufficient. All right, so what I'm going to do now is I'm going to come back to my input. And I'm going to double my input from 250 millivolts to half a volt. Now, if this was a normal linear amplifier without any compression, I would expect to see double this signal. This 166, let's call it, 167, would get doubled, right? So we'd be looking at, somewhere around 330 or so millivolts if this was a normal linear amplifier. Let's find out. Okay, I'm going to separate these out again. Now notice our control voltage up here, right? So, this is actually, you can see kind of what's happening here. It's grabbing the signal, it's leveling out, another peak comes in, we finally grab it after 2 full cycles, and now it's holding at this level, right? So there's 0 volts, minus 3, so it's, somewhere around like negative 2.5 volts. So that should, as a VC, it's more negative, we should have smaller gain, right? What do we get? Here's my nice 500 millivolt input. Here's my output. Let's go grab a peak. And, all right, so we're getting like 266, which is not double, right? I doubled the input, and we went from over here, 166 and change, which, like I said, should give us like, 330 or so. But instead, we're getting 266. So that output change has decreased compared to what the input change was. Not much, it's like a couple of dB, but that's what's happened, right? 6 dB input change, and there's a couple of dB output change. Reduction. Let's do it again. Turn it into a volt. So I'm going to double it again. Oops. Bonk. All right, separate these out again. Okay, you can see the control voltage working its way down. This is essentially the attack on this thing, right? It works its way down, and now we're coming down to about minus 8 volts, So the gain should have gone down even further. Here's our nice 1 volt input. Here's our output. Now, before I actually measure this, note what's happening right here at the beginning. Right? This signal starts off pretty big and then gets compressed down, right? It takes a while for the compressor to sort of stomp on this thing, to stomp on the gain. It's not instantaneous. Okay? So, if you're a bass player, sometimes bass players use compressors to enhance the cut, the pop. Okay? And this is essentially how it works, is you get this increased attack over here. All right? Anyway, let's see what happens with our amplitude. All right, what are we getting there? 268, I think is the, yeah, so we're getting like 268. Now, remember, this is 4 times what the original input is, right? We started off with 250. We're now at 1 volt, so I've increased it by a factor of 4. Our original output signal was 166. Now, if you quadruple that, right, you're looking at like 650 millivolts if it was a normal linear amplifier. But we're only getting 268. We're not even getting twice. Okay, so we can definitely see how this thing has reduced the output gain. We've compressed that signal. All right, kind of cool. Now, if, like I said, you want to breadboard this, just beware of a few things, okay? Like I said, the 13700 here doesn't have a very high input impedance. It's really set by Rn, so if you're going to hook this up to a guitar or a bass, you're going to want a little buffer amplifier up here to give you a high input impedance. These two, you could use a dual. I've got 081s in here, but an 082 or a 353 are nice, affordable, well-behaved bi-fed op amps, okay? That would work well. Like I said, RF, you would probably want to make a pot, turn that into a rheostat. You may or may not want P2. If you're going to simulate this, it's worthwhile to kind of monkey around with this. Like I have a slight positive bias on this. If you bring the bias down, then, like I said, the range of compression is going to alter a little bit. So you might like that. You might not like that. You don't set these things by the number, really. You listen to it, okay? So, that's, like I said, a dual package. Not a lot of components. You might want to, like I said, maybe put a couple different caps out here with a switch so you can have different release times on that. Other than that, it's not too bad. You might want an output buffer. That's probably a good idea. I don't know what you're going to drive with this eventually. And you could even have makeup gain in there because the compressor might produce, this reduction in output signal so that your output could be notably smaller than your input, all depending. So we have what's called, the concept of makeup gain to bring that typical level, that nominal level, back up to a decent level. So, you could use a quad op amp now. Use something like a TL084 or an LF347. Use two for here. Use another one for the input buffer. Use another one for the output drive. Okay, and you could make that adjustable. You could just our load here. You just turn this into a little pot, tap that off, go into a unity gain buffer on the output. Boom, off you go. All right. Okay, there you have it. A little bit different than your usual, light dependent resistor, maybe JFET ohmic resistance kind of thing. But it's a compressor. Play around with it. Have some fun. Have any questions? Or, hey, if you do build it and you have some commentary to make, things you altered, you liked or didn't like, put them down in the comments, right? Share them with your fellow devotees. And with that, I'll say goodbye for now. See you next time. Take care.